Let's continue with the discussion of the concept of angular momentum. One of the most spectacular examples is an astronomical object called Pulsar. What's a pulsar? It's a shorthand for a pulsating star. It was first discovered in the year 1967 by a graduate student. What he found was a radio frequency from space which had extremely regular frequency. So the frequency is very, very accurately a constant. Because of the constancy of the frequency, people speculated that this signal may not be, produced by nature, which probably would be more random, it would be fluctuating, but rather it could be from something that is extraterrestrial intelligence. And of course, very interesting, so people started to investigate. Okay, a long time has passed since the year 1967, and now scientists have a better idea what this pulsar really is. So here is the story that scientists believe now. You start with a sun, with a star like our sun, okay, that has a certain radius, r initial, mass m, and it is spinning about a certain axis with an angular speed of omega initial. You start with a sun, not our own sun, but somebody else's, in some other solar system maybe. There is a star whose mass is a little bit greater than our own sun, maybe, maybe twice the mass of our sun. Okay, and it spins, say at a rather slow rate. Our sun, currently, the surface of the sun turns around every 30 days or so. Okay, but this is when the sun is in the early stage or middle age, when there is plenty of nuclear fuel to burn. Our sun, for example, is middle-aged. But what happens when a star gets old? When a star gets old, the nuclear fuel that drives the radiation outward is depleted. Okay? And yet the sun still has most of its mass intact. So as a result, what happens is that you have this gravitational inward pull because of the mass, and yet the outward radiation can no longer balance the inward pull. So therefore, gravity wins and the star starts to shrink. Shrinks to something much smaller. Okay? And then as it shrinks, what happens to the angular speed? That's what we want to know. The star is pretty much an isolated object. Okay? It is pretty much an isolated object. So we can pretty much safely say that the gravitational, except for the gravitational force from other stars, which can be pretty far away, there is no that much external force. And then, of course, there's no external torque either because the force is equal to 0. And what that means is that the angular momentum of that star should pretty much be conserved, right? How do you calculate the angular momentum? Well, it's I times omega. If you roughly treat the star as a rigid body, it's I times omega. So the initial angular momentum is I initial omega initial. And the final angular momentum, when it becomes much smaller, okay, if the radius is r final and it spins with omega final, that would be I final omega final. And since in the process of shrinking, the only force is the gravitational force, right? That pulls the star material in, make it smaller. That, of course, is an internal force. It does not change the angular momentum because only external force that produces external torque can change the angular momentum. So we say you have a conservation of angular momentum. Okay, how much smaller would it get? Well, that turns out that depends on the mass. The more mass you have, the more gravitational pull to pull it in. Our sun, for example, when its nuclear material gets depleted, after a couple of billion years from today, it's going to shrink to something about the size of the Earth, like a planet. Okay, like a planet. And for some other stars that are bigger to begin with, that are more massive to begin with, let's say 1.5 or twice the mass of our own sun, it's going to shrink to something even smaller because the incredible gravitational pull. Our sun, when it reaches the size of a planet, we call it a white dwarf. A white dwarf. It's a dwarf because it's a lot smaller than a regular star. And it's white because it emits all kinds of colors, so it appears to be white. But for a star which is more massive to begin with, the gravitational pull will make it even smaller. It will shrink to the size of a small city, believe it or not. Okay, that omega final will be even greater because the size is even smaller. And R final would be of the order of a few miles. Can you believe that? You may have heard that when the star shrinks to such incredibly small size, the density is so high that the protons and electrons are squeezed together to form what's called neutron. So the whole thing is made of neutron. We call it a neutron star. Okay, a neutron star. How fast does it spin? Well, we can roughly figure out the rate of spin using the conservation of angular momentum. You know, I initial, if it's a uniform sphere, that will be equal to 2/5 of mr squared, right? Of course, it's not quite uniform, but roughly speaking, we know that I initial should be proportional to the radius squared times the mass. Let's say the mass doesn't change by much, so it's the radius, okay? So I should go like radius squared. So I goes like radius squared. Okay, what about the frequency? Well, suppose I know the time it takes to turn around, okay? The time it takes to turn around. The angular frequency or angular speed. Okay, how do you figure that out? Well, you know, angular speed is the rate at which the angle turns. All right? Suppose you turn a whole angle of 2 pi. 2 pi. That's one revolution, right? 2 pi. How long does it take to do that? Let's say the time it takes to complete one revolution is t. You finish this angle 2 pi over time t. So 2 pi over t is the angle covered divided by the time it takes. And that, by definition, is the angular speed omega. All right? So you see, omega goes like 1 over t. What's t? T is the time it takes for one revolution. It's also called a period. Okay, the outer surface of our sun currently has a period about 30 days, 30 Earth days. Okay, if we plug these, expressions into here, what I get is a relationship between the radius and the period of a rotating star. And here is what it looks like. I goes like r squared, omega goes like 1 over t. So this is r initial squared over t initial equals r final squared over t final. Okay, we can solve for t final, right? We can solve for t final, and let's see what we get. That is the final period. That will be equal to initial period times a ratio, and that ratio is equal to r final over r initial squared. Right? Okay. Let's use the data from our sun because it's a typical star. Okay, we have about 30 days here. Now each day, you know how many seconds are there, right? It's 86,400 seconds. Let's not be too picky. Let's say, it's just about 80,000 seconds. So it's 30 times 80,000. That's 8 times 10 to the 4 seconds, right? 30 days times the ratio of R final over R initial. What's R final? Well, that depends on whether it shrinks to a white dwarf and stops or whether it continues to shrink into a neutron star. If something has, about 1.5 to 2 times the size of the mass of our sun, it's going to shrink to a neutron star. And for a neutron star, we're looking at a few miles of radius. So therefore, in terms of meters, the final radius is about 10 to the 4 meters only. The initial radius, that's the current size of the star. For our sun, for example, the value is about 8 times 10 to the 8 meters. So let's say 10 to the 9 meters. Let's just get a rough estimation here. You square it. Okay, look at this ratio here. 10 to the 4 over 10 to the 9. That's 10 to the negative 5. You square it, that's a whopping 10 to the negative 10. In other words, the final period is only about 10 to the negative 10, or 1/10 billionth of the initial period. And if you work this whole thing out, you find the answer to be about 2 times 10 to the negative 4 seconds. Think about it. Right now, it takes 30 days to go around, okay? Because of the conservation of angular momentum, as it shrinks and shrinks, you lose rotational inertia. So to keep the angular momentum, omega has to pick up. You're going to go faster, spinning faster and faster and faster. As it shrinks to the size of a neutron star, only a few miles across, it is only going to take 0.2 millisecond, okay, 0.2 millisecond for you to finish one revolution. So it's basically a rapidly turning neutron star. That's what it is. Okay, so when a massive star dies, it becomes a rapidly turning neutron star. We can exactly figure out the final period or final turning speed using the conservation of angular momentum. You see, it does not only apply here on Earth, it applies to a remote corner of the universe for a fast-turning neutron star. And as it turns, it has a strong magnetic field. Okay, so as it turns, the magnetic axis turns around, producing an electromagnetic radiation, and that is the radio signal that was observed. And since the period of turning is precisely determined by conservation of angular momentum, it cannot be any smaller or any greater. It is precisely controlled by conservation of angular momentum. So the period of turning is highly constant, extremely constant. As a matter of fact, the constancy is so remarkable that if you use a pulsar, okay, use the frequency of a pulsar as a reference for a clock, that clock will be so accurate. It is better than the most accurate atomic clocks that we can produce here on this planet. It is the most accurate clock that we know in nature. And it is all thanks to the conservation of angular momentum. And by the way, the final period here is what we got is about 0.2 millisecond, but you cannot take this number too seriously, 0.2, 0.3, whatever. A lot of pulsars are observed with a period in the millisecond range, so these things are called millisecond pulsars. Okay, you can understand why we have a lot of millisecond pulsars, because we look at some typical numbers, we find that, as it speeds up in rotation, when it shrinks to something, only a few miles, you're going to get a period of rotation about, in a millisecond range. So that is a spectacular application of the conservation of angular momentum in astrophysics.